Welcome back to the series of lectures on high performance scientific computing. In today's video, we will revise a few concepts on how to improve performance by looking at some theoretical work, and then we will actually implement that theoretical knowledge into trying to analyze our code practically. So first, let's begin with some theoretical understanding. So let us now have a revision of the basic units that we have worked with before. You have n, the variable, which is the problem size. P is the number of processors that you have, which you can use in parallel. We know that every program or every algorithm has some inherently sequential portion which cannot be changed, and let's say sigma, which is a function of n, the problem size, is that inherently sequential portion of computation, i.e. the time it takes, and that time could depend on the problem size as well. This particular part of the code cannot be parallelized whatever you try. Then you have the portion of the code which is parallelizable, which is psi of n. Again, this will have a functional dependency on the problem size. We also know that more the number of processors, the larger the problem, we will incur something called as a parallelization overhead. Let's say k or kappa is a function which depends on both n, the problem size, and p, the number of processors. Obviously, the speed up that we want, psi, is a function of both the problem size and also the number of processors we end up using, and it is essentially what would be the sequential execution time divided by the parallel execution time. For ideal cases, this should just be n, right? It should be p, because as the number of processors increase, this ratio should keep on increasing ideally to p. So if I have 10 processors, I should have a speed up of 10. If I have a processors 128, I should have a speed up of 128, but that's rarely the case. Finally, we've tried to measure what the efficiency is. The efficiency is again a function of n and p. It is a sequential execution time divided by the number of processors used into the parallel execution time. Now, if the efficiency turns out to be 1 or 100%, that means you are getting perfect linear speed up. But again, we know that we are always running below the ideal efficiency. So our sequential execution time technically will not be the same as the number of processors used into the parallel execution time. In fact, it will be somewhat slightly less. So this efficiency number will be generally less than 1 or generally less than 100%. Now, we know the sequential execution time, which is basically for the p is equal to 1, which is essentially t of n comma 1, is sigma n plus psi n. Now, let us assume that the parallel portion of the computation that can be executed, it divides up perfectly among p processors, right? Sometimes with irregular problems, that is not the case as well. But let us say that we have a problem which is fairly regular and can be perfectly divided amongst p processors. So then the parallel execution time, which is a function of both the size of the problem n and the number of processors p, is at minimum is greater than or equal to the serial execution time for n plus psi n by p, which is the parallelizable time divided by the number of processors p, and plus whatever overhead costs we are incurring, which is kappa n comma p. Now, the speed up will be less than sigma n plus psi n over sigma n plus psi n by p plus kappa n p, and efficiency is now just going to be p multiplied by the denominator of the speed up, and that's how you would compute the efficiency. We now revisit Amdahl's law. We say if the parallel overhead of k and p is neglected. So this is another assumption that we are making. We're saying that all this parallel overhead, usually which comes up practically in terms of the cost of communication, the cost of setting up all the parallel communication, etc., that is neglected. We say the speed up is now minimally, or rather at most, So sigma n plus psi n over sigma n plus psi n by p. Now, if f is the percentage of inherently sequential portion of the computation, like if f is sigma n by sigma n plus psi n, then Amdahl's law can be written as the speed up, which is going to be 1 over f plus 1 minus f by p through this derivation. Now, f is a number which is always bounded between 0 and 1. So, f is the fraction of the code which is parallelizable. So, that means that fraction could be 0, that means none of the code can be parallelizable, or f could be 1, that means the program is embarrassingly parallel. So, the maximum speed up that you can achieve now is 1 over f into 1 minus f by p. Now, as p tends to infinity, let us say that you have infinite number of processors, the maximum speed up that I can get to is 1 over f. This has surprising implications. Let us say my code is 50% parallelizable, my maximum speed up is only about 2. Let us say I am 90% parallelizable, only 0.1% of the code is sequential. At that point of time, you have a maximum amount of speed up which will asymptote to about 10. Now, where does this come in a practical sense? So, typically we start off with a serial code, and then taking the serial code, we have to now start implementing the parallel algorithms for that particular serial code to achieve certain speed up. Now, this graph and this theoretical analysis clearly tells us that if the sequential part of the codes are large, then there is no point trying to parallelize it, in the sense that if you cannot parallelize certain bits of code, and if those segments are large, there is no point trying to put any effort in that bit of code. So, we need to figure out, the first thing that we need to figure out is which part of the code takes how much time, and we need to have a proper analysis of this. This is where the profiling tool comes into play. So, what is profiling? It essentially is trying to measure the program execution. What you're trying to figure out is where the code spends most of its time. Is it spending time in function A, in function B? Is it spending time in doing memory transfers? Is it spending time doing some hard computes? So, we are trying to figure out what these performance bottlenecks are. So, we need to profile this code or any code that we want to parallelize thoroughly. Then we go about optimizing this code for its speed and its efficiency. We also want to understand what the program behavior is underneath. Obviously, we want to profile before we undertake any task of any major optimization of the code, because let us say that most of the code is spending its time only in one function, then we want to possibly concentrate on that function and improve the efficiency of that function. There might be another function which can be parallelized easily, but the code barely spends any time over there. So, maybe it's not worth your effort to go and actually parallelize that code, because its impact might be nothing. So, this is all critical when it comes to improving major performance. So, we will now in the next few videos see what these different profiling tools are and how about we can go about this profiling process. So, the first profiler that we will look at is something called as gprof. This is the GNU profiler. It's part of the GNU bin utils suite. It essentially what it does, it analyzes the program execution time. It gives a nice flat profile. It gives what is called as the call graph information, where you can see which function is being called when, which function is being called by which other function, and you can look at the entire history of it. You can get statistics like how many times a function has been called. You can get statistics like how much time is being spent in each of the function. This is a very simple tool. It has been around for many years, but it is very useful in many cases. So, how do we go about using gprof? So when you're using gprof, when you're doing the standard compilation of the code, the device code which is generated underneath does not have any information for doing any sort of profiling. You need to actually specifically instruct the compiler to add what are called as profiling object counters, or you need to compile it with the -pg flag. This will put additional information in your executable to do this sort of accounting business, where you're able to keep track about which function is computing, is being called how many times, how much time is being spent, etc. Once you compile the code with the PG flag, all this sort of information is now good to go within the executable. Then when you run the executable, another file called gmon.out is being generated, which has all this information during the execution of the code. Remember, you have to run the code once and only then you'll be able to get the profile, because just merely looking at the code without having the inputs, etc., the compiler is not going to figure out how many times each function is being called or where the code is spending most of its time. So you need to then run gprof on the executable, and then you need to go and analyze the output. So how do we do this compiling for profiling? So let's say that you're using either GCC or G++. You will say GCC -pg, you will give it an executable name, in this case -o my program, and whatever the source code is. If you're using G++, or rather if you do C++ programming, you'll just use the compiler G++, and PG flag will now add the profiling code to the executable. This code will now record all the function call counts and execution time. Once the compilation is done, you run the compiled executable normally. The gmon.out file is created in the same directory, and this file contains the profiling data where the execution is done. And finally, when you want to generate the report, you do gprof my program. It usually will spit out a whole bunch of information. It's generally good to redirect that output to a text file so that you can save it and review it later. And then gprof, what it does is essentially it reads the gmon.out file, and then it reads the executable which has all the instructions and generates the report with the profiling instructions. We will now see how to do this in a practical way. So we will now first look at our old Laplace code. We'll see what are the functions inside it. We will see how to compile it and make it ready for profiling, and then we will finally profile it. We will now only begin with the serial Laplace code, because this is where we want to begin, and we want to then identify where the code takes most amount of time, so that then I can focus my attention and my energies in parallelizing those functions only and not any other function. Let us now look at this Laplace code. So if you recall this, we were trying to solve the problem of heat transfer on a flat plate. We had a square plate where two edges were kept at the temperature T is equal to 0. The other two edges, the right edge and the bottom edge, you had a linearly varying temperature from 0 to 100, and we were trying to compute the internal distribution of temperature using something called an iterative method called as the successive over relaxation technique. So here we are defining the number of columns and number of rows, or the number of unknown points, the internal points, to be 1000 in each dimension. So we have 1 million unknown points. We have the maximum number of iterations that we want to do for this computation to be about 1000. In the code, we had already put in some OpenMP directives while we were trying to parallelize it. We will check whether if those OpenMP directives are there. If they are there, we will remove it temporarily, and then we will go ahead and just profile the pure serial code just to see where the code spends most of its time. You can now see that there are many functions over here. You have a function which is initialize, which is doing the initial step of initializing all the initial variables. You have a function called set boundary conditions, which is setting the boundary values, especially for the right and the bottom edge, from 0 to 100 linearly. Then you have a print trace function which periodically puts out the output. You have the compute function which is actually doing bulk of the compute per iteration, and then you have a copy function which is copying the value from the previous iteration to the current iteration. So if you look at it, the code starts, you first call the initialization function, which sets the initial guess to 0. Then you have the set boundary condition over here, and then you copy a certain set of values into TOL, so you have both your arrays ready, and then this is where you start the number of iterations. So you say that I'm going to do 1000 fixed iterations over here, and for each iteration first you're going to call the compute function, then you're going to call the copy function, and then periodically every 100 iterations you're going to call the print trace function. So the compute function essentially does the average of your 4 neighboring points, the 4 neighboring points being your north, south, east and west, or I plus 1j, I minus 1j, ij plus 1 and ij minus 1 points, and you're just taking an average of those points. So that is the compute function. What the copy function does is that it copies the computed values into the previous old values so that it is ready for the next iteration. And this is the cycle that goes on. This is the initialization function which we talked about. This is the boundary condition setting function which we talked about. And finally, we have the print trace function which prints out the last 10 diagonal elements. First, now let us compile this code and run it, and then add the PG flag to while we're compiling it as well, so that we get the counters for doing the profiling. So the way we compile this code is GCC minus PG Laplace serial, and in this case I do want an output going to Laplace serial, right? So now I have an executable which is Laplace serial, and I am going to now execute this code. You can notice that there is a previous gmon.out from one of my earlier tests, but this was done about 20 minutes ago. So now we will run this code directly. So we need to run this code, and you need to replace and generate a new gmon.out file. So for proprietary sake, I'm just going to delete the old gmon.out. And you can see that it has now no gmon.out, and the Laplace serial now will create a new gmon.out file. So now let us execute this code. Okay, the code has now been executed, and you can now see that a new file gmon.out has been created to put all the information from the profiling. Let us now profile this code. So if I just to profile this code, I will say gprof and the executable name, not the gmon.out name. So I'll say Laplace serial. So the moment I put this, you will see that the code has sort of gone and spit out a lot of information over here, and instead of sort of it running away every single time, what I'm going to do is I'm going to redirect it to a text file. So I'm going to just redirect this to Laplace serial profile, so which gives me a text file where I can read this information at my leisure. When I open this up, now I will see a whole bunch of information. So now you will see that this is a total flat profile which is being done, and you see that you get information about the function compute, and the function compute takes about 4.12 seconds by itself. The copy function takes 3.12 seconds by itself, and then you have 1000 calls each of the compute function, 1000 calls each of the copy function. So this makes sense because we are doing some 1000 iterations, and in each iteration we are calling compute once and we are calling copy once. We also notice that the time taken by the compute function is 56.83% of the time. The copy function takes 43.03% of the time. The initialize function, which is called only once, takes about 0.14% of the time. The print trace function, which is called 10 times, barely takes any time, so that it says 0% because it's barely measurable within the decimal accuracy which is there. So is a set boundary condition function. Now you can see when you add up whatever the cumulative functions turn out to be. So it will come out to about 100%. With this information, I can now deduce the fact that the code spends most of its time in the compute and the copy functions. So this is where I really need to focus my effort in parallelizing. There is no point trying to parallelize something like the initialize function, which takes only about 0.14% of the time. So if I focus my efforts first on the compute function, which takes 56% of the time, then I should at least be able to get reasonable speed up, and the maximum theoretical speed up that I can get is 1 over 1 minus, or rather 100 minus 56.83 divided by 100. So I should be able to speed up if I first parallelize the compute function. After parallelizing the compute function, the next effort I will do is trying to parallelize the copy function. And you can see between the copy function and the compute function, this code is spending nearly 99.86% of its time over there. So you can clearly say that this code theoretically is extremely parallelizable, because all it is doing is a bunch of independent computes and an independent bunch of copies. So this is as close to embarrassingly parallel that you can get in terms of the code. So if you go down, you'll get to see a little bit more information. You'll see the definitions of all these things, and then you will also see another call graph. A call graph here essentially says that this is the first call graph is the function main. The main function obviously takes up the entire 100% of the time, and in that, the main function, main is calling compute 1,000 times. Compute has been called 1,000 times, and all of it by main. Then copy is being called 1,000 times, and all of it is being called by main. Initialize is being called once by main. Print trace is being called 10 times by main, and set boundary conditions is being called once by main. And you can see the breakdown. Now, the functions underneath this call graph, they're not calling any subsequent functions themselves, because they're just doing the compute, right? So you can just look at the breakup of time there. Now, it's quite possible that functions themselves will call functions, and it's quite possible that two different functions might call the same function. For example, you could have a function A, which is calling a function called compute. You could have another function B, which is also calling compute. In that, the total number of calls for compute might be the sum total of calls of function A and function B. So that will also be reflected in this call graph if required. So if you have different functions calling a common function or multiple functions calling each other, all of this can be shown on this particular call graph. So this is how the explanation of the call graph is. So here also you get information that how much of the time is being spent on the self or the main function, and how much of it is being spent on the children of that function. So if compute is going to call somebody else, how much time is being spent by the children of compute? How much time is being spent by the children of copy? In this case, there are no further children of compute and copy, because they themselves do not call any more functions. So this is the total index, and you can then read through this entire prose to figure out what each of these values mean. So this is a very simple code for Laplace serial. You can have very, very complex programs which have hundreds of functions which call each other, and then you can clearly get an idea of where to put your effort in terms of parallelizing. So first, you need to understand what the flat profile is. The flat profile basically tells you the percentage of total time spent in each function, the cumulative seconds and the seconds per call, the function name and the call count. Then the call graph tells you what the call relationships are and what the individual call counts are for each of those functions, the percentage of time spent in each function and its children. And you also need to identify which function causes the bottlenecks. So you can then figure out where you can put your effort. Now, what are the limitations of gprof? Whenever you add this profiling information, it obviously affects the program performance. Essentially, what you're doing is you're introducing a little bit more of device code in your executable to put in these counters, right? So when you put these counters in, they obviously are going to consume some more time, and this can affect the program performance directly. A code which is not having the -pg profile or -pg as a compiler option will generally run faster than when you do profiling. If you have very short functions, there could be some inaccuracies in timing, and gprof has very limited support for multi-threaded and OpenMP programs. We will discuss another tool called Valgrind for that. There are very big limitations with shared libraries. We see that in many programs we call other libraries, and within those libraries there could be pre-compiled functions. So that gprof is unable to get to very conveniently. And obviously for very short programs it's not very accurate, but this should not really concern us because typically for high performance computing we have large programs. What are the key information? So we can say that gprof is a valuable initial tool for performance analysis. It's something which is very quick, which a programmer can do very easily and very fast. We can understand the flat profile and we can understand the call graph, which is very important. We can use gprof to identify and optimize the performance bottlenecks. And this is a very crucial part of any sort of software development, whether you're doing just serial programming or this is your first steps towards parallel programming. Thank you.